Today I'm going to talk about a paper in 1951. It's maybe the beginning of these types of algorithms, stochastic approximation algorithms, and then it has many uses in the following sessions. We'll see the usefulness of these type of algorithms. In this talk I decided to just focus on this single paper, that it's maybe the very biggest steps of getting through this topic. It might be very familiar for many of you, but anyway. So first we're going to begin with the problem statement. So in a very simple problem, let's say you want to find the root of the function f of x, and then so one conventional method is using the Newton procedure. So we begin with point ti, and then we did this iterative procedure to find the root of the root theta, which is asymptotically, so this theta n is asymptotically convergent to that theta of the root. And this is very natural, and then you all know the intuition behind it. And the thing is that this factor behind it, it's going to be decrease and decrease, so that you take the smaller steps as these iterations go forward. So, but we are looking for maybe alternative approaches. So maybe we put some conditions, some mild conditions, then we can work on a different approaches. So if we have that for a neighborhood around this solution, if the f of theta is smaller than 0, so we are looking still for the root. So if this f of theta is smaller than 0 for the values smaller than the solution, and it is positive for values above the solution, and the f is non-decreasing, so we can use such algorithms that iteratively each theta n plus 1 is the theta n minus a factor alpha, which is constant here, times the value of f of theta n. So this means that at each steps we use the same line with the same slope, but we hopefully get to the final answer. And so one intuition also can be what happens if this function f is equal to derivative of another function, then it is like this gradient descent algorithms that we have in optimizations. So this is like a general formula. If you can solve this type, then you can use it for the following optimization problems. So there are some challenges. So let's say if I don't have access exactly to these values of fx, this could be one challenge. Or the other challenge could be that it is costly to take the experiment. So if x is an experiment and f is the outcome, let's say if it costs for us that we take x and we take the experiment, and we don't want to use that, so then we might go for a noisy version of f instead of having the f exactly. So the challenges are, let's say we have noise. So instead of when we want to measure on theta, the outcome would be a noisy version of the f of theta, which is y. And then obviously one way of dealing with such an error could be that we take an average. So we do this experiment. So let's say we want to do this finding the root thing, and then we say, okay, we begin with this ti, and then the outcome of ti, if I put the theta I here, then the outcome would be yi, and then I repeat it for n times, and then I take the average. Hopefully this effect of noise would be vanished, and then I get an average value of f of theta. Then I can use it in my iterative algorithm, this one, and go on for finding the next thetas. But this might not be this could be a good approach, but as I said, it might be costful to take this approach and take this experiments of finding yi. So then, in that case, we don't want to like use our resources to just taking the average for maybe non-relevant point. Instead, we want to go faster to the main point and then take the multi-accretions in the neighborhood. So that is one intuition to not to choose these types of algorithms. So this paper that this is the main paper that I was going to present was by Robin and Monroe in 1951, and they suggested this algorithm. This is still for finding the root. So the theta n plus 1 equals theta n minus now a gamma n times yn, and this gamma n is actually a sequence that decreases over time. For instance, it is 1 over n plus 1. And it has to have some properties, like the gamma n should itself be convergent to 0. As I said, we want at each step we want to have slower and slower gradient rate. And then we also this is one property that proved in the paper that we needed, that the sum of these sequence should be infinity, so it should be divergent. And also the yn, so again the yn is a noisy version in our scenario, is a noisy version of this f of theta with the noise of the n, that we assume it is 0 mean and it is IID. And maybe it's good to, because these types of algorithms is useful, maybe it's good to have an intuition with an example. This example, it does not really relate to this problem, but it gives you an idea about how this iterative thing may behave. So let's say we want to find the average of the thetas. So forget about this problem. Let's say we want to find the average of these theta. One way is just taking n samples and then take the average in the end of the experiment. What another approach could be that you find an iterative formula like that it is an online averaging. So at each step, the output, the theta is actually the average of these parameters yi. So if I do this iterative algorithm, and if I take the gamma n to be 1 over n plus 1, then what would happen is that the theta n at each step would be 1 over n of summing of these yi. And then obviously by converging, by asymptotically, it can go to the mean of these yi. So this is just, I mean, if you just insert the y over 1 over n plus 1 here, you can see that this is happening. So this is like an intuition behind the using of such sequences to this gradient descent algorithm. So this is a motivation example that is studied in that paper. So let's say we want to find, so now instead of root, now we are focusing on any value alpha of a function f of theta. So we have an unknown distribution. So this f is a distribution function, and we want to find the f of theta equal alpha, and then we want to find this theta, which is the solution. And let's say we have the property that is always positive at the point of solution. And then let's say we have a sequence of Zn. So let's say that we cannot observe the f of Zn. So we don't have access exactly to the f of Zn because it is, let's say the experiment was costly for us. But what we can do is that we can experiment on another sequence xn, which is somehow related to Zn, and then we can see the observations yn. So this is like an this looks like a noisy version of f in the previous example, but so we characterize this yn as let's say the indicator of zn is smaller than xn. So let's say we are not seeing zn exactly, but what we can see is just experimenting on xn and observing yn. And what we're interested is finding this solution theta, which is the solution of f of theta equal alpha, without doing experiment of zn. So I don't know whether I explained this well, or if there is any doubt, I can explain it maybe better, or is it clear? This is just one example that we can use the algorithm, and then this algorithm actually answers that how to choose this xn's, so that by experimenting and observing yn, this xn actually converges to this theta. So we need some assumptions for the algorithm to work. And the first assumption is that the function mx should be monotonic, and also be defined for now. Let's say so in this previous example we were working on this fx. So this was just an example. But now in the main algorithm, let me introduce this mx to be this expectation function. So the mx is a monotonic function, and then we want to find the root of the solution of mx equal alpha, and the mx is equal to this expectation over a distribution. So with respect to this distribution of y given x. So this is the expectation of y with respect to the distribution y given x, which is given here. But the thing is that the f is unknown to us, so we don't have the function m, and we don't have the distribution f. And with all we have, we want to find the solution for x, and we want to just do this iterative algorithm. And in the end, so what we are interested is to choose some xn and observe this y, and then we want the xn to converge to the solution theta. So the first condition we need is that this y should be bounded somehow. That if you put this bound c for the values of y, then you're sure that we have covered all the values of y, in the sense that the summing over these probabilities should be 1. So we need this bound over the y, and we take some. So this an, this is a sequence like the gamma n we introduced in the previous slides. So this an is a sequence that it has this property that the summing over the squared is equal to a, which is a constant and which is smaller than infinity. And then the main procedure is this, that the xn plus 1 minus xn equals the sequence, the an, times the alpha minus 1n, and the alpha was if you recall, is the solution of mx. Not the solution, but the value that we were interested to find a solution for. And then yn is obviously the realization for y at each point of xn. So what you're interested is that in the end of this algorithm, this error between the xn and theta converge to 0. So this means that then asymptotically xn is converging to the theta. And the whole the art of this algorithm is to find this sequence of an such that this whole thing works. And recall that we don't have access to exactly the value of f and the function of m. So we don't have that. So here I'm going to just explain the proof. So let's begin with this two definitions, dn and en. So the dn is the expectation of xn minus theta times this one, and I don't know whether I have put it in the slides or not. No. So if I assume that the mx, so if I assume that the mx is larger than alpha, for x is larger than theta, and mx is smaller than alpha, for x is smaller than theta, then you can see that this is something always like positive, right? Since if this is positive, this is also positive, and if this is negative, this is also negative. So this is the expectation of some positive term. And the En is also the expectation of this y minus alpha squared with respect to the distribution of y given x. So with doing some calculations, we get to the point that I think this is a typo here. So we're doing some calculations. We get that this error term, this b, if you recall, was the error. So this bn plus 1 minus bn equals an squared en minus 2an dn. And then, as I said, since this ei, this is obviously a positive term. So, and also since the ai, the sum of ai, we assumed it to be assumed to be a finite value, then this summation is also finite. And then it is resulted that this sequence, if you take this to the other side, this sequence is also a finite value. So it is like converging to a value like b, which is smaller than infinity. And then, so if this is a finite value, then it means that there. So for at some point of time, then this bn converges actually to this bu, which is a finite value. And we need to prove that this b is actually 0. So the error is converging to 0. So here we said that this is a convergence. So this summation of ai di is a convergence, a finite value. So we say that there exists a sequence kn. This should be larger than equal. So this is a typo, sorry. So we assume there's a sequence kn such that the dn, which was the expectation of xn minus theta times this. So this dn is larger than kn times dn. So we want to, in the end, find this sequence of kn, but first we will study some properties. We want to find the properties of kn. So then, since dn is larger than this one, using that we can see that the so this is some properties over kn. One is that dn is larger than kn bn, and the other one is this summation is divergent, so it is equal to infinity. And using the property 1 and this one, we can see that if I just substitute, we can see that the summing over an dn is also is convergent, so it's finite. and also using 3 here, which is this is infinity. So we can say that for any epsilon, then there are many values of Bn which is very small. So let's maybe it's better that I do the calculations on the board. So we have that this A and Kn is infinity. And then let's see what I'm missing here. Let's begin with the first one. So, since the A and Dn is larger than A and Kn En, so I just multiplied Kn here, then summing over this would be larger than summing of this, and we said that this is smaller than infinity, so this is the first. Okay. So let's say we have this one, that this is smaller than infinity, so this is a constant value. But meanwhile, we took this sequence of Kn such that the summing over A and Kn is infinity. So it means that then this Bn should, at many points, it should be very small, that cancels the large values of A and Kn, so that this whole sum would be bounded. And this is the reason that for many points of n, the Bn should be very small. Right?
That's true, but I guess that there should be some part of the proof that says that the set of possible Kns are non-empty. So there is at least one Kn that can satisfy.
Actually, in the rest of the proof, we like prove that there exists, and we determine the Kn.
Can I ask something? You have equation 1, and in the third bullet you have from 1 and 2 the same equation, right?
So yeah. I was looking for what I missed. Let me see. Sorry, I prepared this slide in the last minute, and there might be many typos.
Maybe there is some Bn inside there.
In the paper it says AN, KN, BN.
Right.
Mm-hmm.
Yeah.
Yeah, maybe.
Makes
Yeah.
sense.
So this is the same thing. Yeah. So this is the same thing that we said here. That this is bounded. So yeah. This should be A and K and B N. Okay. So these are the properties for Kn that you're interested, and then so we say that if we find such Kn, then we have that this B is converging to 0, and then the algorithm works. So now the problem is that we find the sequence of Kn, and then so for that, let's say we had two properties for Kn, the 2 and 3. So the 2 is that the Dn should be larger than Kn times Bn. So we attack each of these conditions independently. So here we define an upper bound for the values of for the absolute value of x and minus theta. So we say that we are not like deviating from this theta more than an somehow. So this, the probability of this is smaller than an is 1. So this is an upper bound. And then we introduce kn to be the infimum of the mx minus alpha over x minus theta. So to me it looks like the f prime that we did in the very beginning algorithm, that's like the Newton algorithm. So it has the intuition that why we're using this. So if we choose the kn to be mx minus alpha over x minus theta, and then from the definition of dn, we can see that this is always larger than expectation of kn times xn minus theta x squared. So we just replace this one with the bound of kn. And this is obviously because the kn is not stochastic, so we can take it out, and then we have the kn bn. And so we have the condition that the kn bn is smaller than dn with this choice of kn. So 2 is satisfied so far. Now we have to satisfy the condition 3, that the summing over a and kn to be divergent. So we put an assumption that the kn is larger than k over an for large value of n. So let's say in this condition that we have, that mx is larger than so mx is larger than alpha. If you make it more precise and say that so mx is larger than alpha plus delta, and mx is smaller than an alpha minus delta. So what we have is that the mx minus alpha is always bounded with delta, and then we can then replace, since we chose the kn to be this one, so this infimum of this value would be delta. So like intuitively this k is chosen to be the delta, and then the kn should be larger than delta over an. So this is the first assumption that we put for the kn. And the other assumption that we put is for the sequences of an, and we assume that this sequence, that an over summing over a1 till n minus 1, this is the divergence value, and this means that the summing over an itself is also divergent. And an example for this is sequence of 1 over n, and any type of this 1 over n, so like a constant over n, which is c prime and c the second is 2 constants. So these types of sequences, if you choose them, then they meet this condition. So again, I'm going back. So we wanted to say that there exists k and that this is happening. So recall that we chose an to be a bound for x minus theta, and so one choice could be the an to be equal to this value, and by this choice then we can upper bound the value of an with this value. So then, now to characterize the a and kn, we said that we put this condition for kn, that a and kn is larger than an times k over an, and this an is also larger than, is smaller than this value, so we put it here. And by summing over now this a and k, and if we sum over this and this, we take the constants out, since we had that this summation was infinite, then we can see that this summation of a and kn is also divergent. But we put lots of assumptions, right? So we have to meet them all. So one assumption is that this an satisfies like that, but we said that we choose an to be always a function like 1 over n. And we also said that this kn should satisfy the above condition. So another way to express this way of behavior of the function. So what does this function mean? It means that if I plot mx at point, let's say that at point alpha. So it means that it should be above and below, after and before theta. So the function should be something like that. So that's why we can use instead of that we can use this way of expressing the m. So if m is a non-decreasing function and exactly at the value of theta it should be strictly positive, then we can conclude the same convergence. So now let's come back to the problem that I introduced in the beginning. So let's say now my function is, as I said, a distribution function fx, and I want to find a theta that if f of theta is alpha. And as we said again, so we only have access to a value z, we only have access to the value xn, and we can observe yn, and the yn is this indicator function. That if zn is smaller than xn, then it is 1, and otherwise it is 0. So we can only do the experiments over xn. So you can see that the mx was what? The mx was the integral of y d of f of y given x. So it's like the average of y. But you can see that the average of y with this definition is exactly the fx or the fzn function. So here, if we do the algorithm to find the m theta equals alpha, it means that we have find the solution for f theta equals alpha. So now we apply the algorithm xn plus 1 minus xn and choosing the an sequences to be 1 over n, then we showed that the xn converges to theta. And with this example, we can assure that those conditions we need for all sequences an, and the other condition would be met. So we are sure that this is converging to theta. So this is one example that we can use. And if we come back to the problem of finding a root, for instance, then let's say we have now we are putting alpha equal to 0, and then we want to find this theta that f of theta is 0. And let's say we have the noisy version of this f of xn, not the f of xn itself. So since we assume that this is a 0 mean, then mx, if we take the average, so if we take the average of y with respect to that distribution, it is the same value of fx, since this dn is 0 mean. So again, if we use a 1 over n type sequence, here in the literature they use 1 over n plus 1, then we can be sure that this xn with this algorithm is converging to theta. And maybe some remarks. So what we did was we first so let's say we were working on a sequence of zn which we didn't have access to, but we had access to xn and the observation of yn, and they somehow relate to the original sequence zn. So first, in a problem, we have to form this distribution, and then we should check that whether this y is bounded, such a way that this all values of y could be covered within a bound of C. And then we check that the mx, which is the expectation of y with respect to the distribution, what is exactly it is characterizing. So in the previous examples, we showed that the fx is actually equal to the f of x itself, but for different scenarios, it can be characterized different things. And remember that the algorithm actually finds the solution for mx, not the f. But if we form our problem such that the mx equals the value of our intention, then okay, if we find the solution of that, we can find the solution of what we're looking for. And then we have to check for the conditions of mx, which is these mild conditions, like this one, or that the derivative of at this theta should be positive. So these are the conditions that we should check. And then we look for types of an to be 1 over n. So these kind of sequences could help us to form this iterative algorithm and find the solution.
Can I ask something?
Yeah, sure.
That expression there, yeah, is it like this, or do you need a limit from? And you have this subscript n as well in x and y. Because as far as I'm concerned, is like this condition is to ensure convergence in probability, which implies convergence in distribution.
Yeah. I mean, in the beginning, even all the convergence was in the probability.
Yes, of course,
Yeah.
because it's a stronger condition compared to the convergence in distribution probability. But I mean, there it seems to me that you took the asymptotic, not the asymptotic. You took the condition without the limiting, but this algorithm is like an iterative algorithm, right? So it ensures convergence in distribution in the asymptotic sense, which is the definition of convergence in distribution. So I believe there you need some limit with some subscripts.
And they're assuming the f, the conditional f doesn't change. So the y given x is the same
this
distribution
is something
of-
constant. So this is defined in the very beginning,
Okay, yeah.
and we don't
But
know
this
it.
is a condition he gives at the beginning.
Yes.
Yeah. So there exists a distribution that expresses the yn with respect to xn, but we don't know it. But the only condition we have is that this should be bounded as this. And something maybe on the convergence rate. So in 1958, Sachs proved that the convergence rate would be of order n to the power n, so 1 over n. But it is obviously theoretically, so it is very sensitive actually to the choice of the sequence of an. So it is very tricky, and in application you cannot reach this convergence rate necessarily. And then in 1954, so this is something that you can be assured. So if you choose an to be the second derivative of inverse of f over n, so this is of 1 over n type, then if you put the an to be this, then you're sure that the rate is 1 over square root of n. But yeah, getting to this one, you need a really good choice of an, and it's just by theory that this is the convergence rate. Yeah, and that's it. And I know that it's very it's very primary to just study this one, but I think maybe in the future presentations we can work more on these stochastic optimization problems, because this is the basis of these next topics. And yeah, that's it. If you then we can discuss over any doubts that you have or any concerns.
One question. Everything here is just for IID observation as far as I remember.
Yeah.
So what would happen if the observations are not IID first? First question.
So let's look at this scenario then. This one. Let's say we want to find the root,
Okay.
and you say that this yn is f of xn plus dn, so the noise is still IID, right?
No, this is what I'm saying. That what would happen if you relax that to have some other more general property. So not having IID, but having some decreasing dependence between noises. So the noises are not IID, but the correlation would be decreased, and asymptotically the correlation is 0
Between the noise.
between the noises. So the noise at this point is uncorrelated to the noise that happens in infinitely infinite time ago. But the thing is that dn and dn minus 1, they are correlated for sure.
Okay, first of all, I think you have to characterize this thing. You have to check that the mx is still equal to fx.
I don't think so. You need to reformulate it.
Yeah, definitely this form of formulation would not be the right way, I would say. But it's still, I guess that as long as the noise is 0 mean, then the second condition would
Yeah, I
hold.
think this holds, but for the rest, I'm concerned that do we need even something for the rest? Because
Where we have used the fact that the IID.
Sorry?
Where we have used this.
There are
Yeah.
some expectations somewhere that you need to have those assumptions. As far as I
So
remember.
you're always using this f of y given x, and it's always the same.
so it's in
Yes.
13.
Exactly.
Here as well. It's IID.
Then you have fn of y given x, and
Mm.
it gets fun. It can be wrong, I guess. But
Mm. Definitely this has been addressed in the literature. I'm just saying that if you have seen some result on that.
No. I mean, I had time to just look at these convergence rates to just check whether how good is that. And my own concern was that. So let's say how bad. And although I said that it might be not a good approach to this taking the average. But then how good is.
What do you mean by
Yeah.
taking the average?
So here,
This is maximum likelihood estimation, right? 1 over n summation of y. This
Yeah.
is ML estimation, and probably you can do better than that.
but what my concern was that how better is that with respect to the other algorithm? So let's say here in the other algorithm we say that the xn plus 1 minus xn
Hmm?
is equal to some constant gamma n. Let's say if you're interested in the roots, gamma n times the yn. So this is one approach, and the other approach is like taking this and using like in a Newton way, we use the like similar gradient factor. So what is the difference between the convergence of these two? I was curious about that.
Yeah, definitely this maximum likelihood estimation wouldn't tell that this is the best from the convergence rate perspective. I'm not sure even if the Newton is the best for the convergence perspective, right, Sindri?
So I mean, I think
Definitely better than this.
Yeah, exactly.
But this is the first order method, and that's
Newton
the
should
second.
be better. Yeah, I think you also have the typo on the last slide. Maybe you can go, or maybe I misunderstood something. The one about the convergence rates. Yeah, exactly. So the previous one. Right. So here, when you say, so the third bullet point.
Okay.
So here you're using the Hessian, so the second order information, and then the conversion speed is slower than using just the gradient, which is n of minus 1.
but I
It should be n minus 2, right? Or
And it
this is
shouldn't
what I
be capital O, I guess.
But also, I didn't get. So he said something when he talked about the first convergence rate. He said something like that you don't achieve this in practice, or you have to choose the
No,
step-test in a very
yeah.
complicated
So
way. Or,
finding the proper AN is always problematic.
so you say that the result there is saying there exists some step classes, and we don't know which step classes is
Yes.
where we get this very good convergence rate. But then another result is saying that here is a particular step size, and then we get this a worse.
Exactly,
Yeah.
exactly. The proof is not constructive. That tells you this is the best alpha n to get that.
But this is like a,
But-
this is like kind of the best you can achieve or something, the top one, or this is kind of
Maybe not the best you can achieve. Maybe you can find still. I mean,
Or I mean-
this is 1954. I'm sure that they have came up with a better sequences right now. But I think
but this is like a, not a lower one, the top one. Or
this one.
It's like an O,
This
but
one,
big
this
O,
is an
classical.
achievable, right?
Big O result.
but because
Yeah.
but for something you haven't constructed, it feels like a lower one. Or yeah, but it's.
I think they have some weak, they exploit some weak properties like the fact that
Yes.
the summation of these sequences should decay. Some properties like that. They don't have a specific expression for each how you pick each step size. Just some general properties
Yes.
like the limit is infinity or the summation is bounded or something.
But the other,
Yeah.
the other one, if you see, the other one is a function of Hessian. So
Yeah,
probably
but-
in the first bullet, should not be somehow in their proof. It's not a function of Hessian or something like that.
Yeah, but I was surprised to see that the Hessian. I mean, even when you use the Hessian information, the convergence rate is slower. It should be faster.
Oh, because in the first one they say, okay, there exists some
Mhm.
that can lead you there, and in the sample mean it's the rate you get,
Mhm.
right? But
Yeah.
in the second one they say, well, you don't know how to pick it. If you pick this
Mhm.
one, you will get at least that good.
Right, or something
So
achievable.
yeah, the first is
Mhm.
But
nice
if it
to
is
know,
at
but
least
not
as
Yeah.
good, then it
useful.
shouldn't be
Right,
capital
right.
O. If it is at
Yeah.
least as good as this, it shouldn't be capital O, right?
Yeah, or like a
It
different.
should be
Yeah.
omega notation, it shouldn't be capital O notation.
Oh.
Yeah, I'm not sure about the notation, but
Okay.
what I saw was this capital O, but maybe
Okay,
because I took that from like a what was it? It was like a tutorial document that gathered this
Okay.
this thing. Maybe they were
Yeah.
sloppy in the notation. I didn't check thoroughly the paper itself.
yeah, that's
Yeah,
very
of
easy to
course,
find
yeah.
these bounds.
Exactly.
actually.
Exactly.
But Sindri, didn't you see anything about this? So if the noises are correlated?
I have not seen it. There's a interesting problem here, but I haven't looked at it.
Yeah, because for most of the problems that I know, the noises are somehow correlated, actually. And the proofs are coming back to this proof, but the thing is that in this proof, everything is valid for uncorrelated noises. Actually, IID noise is even stronger.
But I think there might be some
There should
Someone should have.
Yeah.
I mean, this is
Yeah,
like a
definitely.
50-year-old paper. Yeah.
because
exactly.
it is very. I mean, it seems very. The steps are very iterative, like intuitive. So I think
Yeah, if
Yeah,
everything
exactly.
is IID, they are. But if you go beyond
Yeah,
IID,
yeah.
then everything would be mess.
Yeah.
So that's the first thing. So one more question.
so. Maybe I mean just.
Yeah.
Sorry to stop you. So I mean I don't know about the next sessions, but to me it's very interesting that we put something on the optimization, a stochastic optimization, to be as a follow-up of this.
Absolutely, we
Yeah,
do have.
exactly.
Actually, I'm not sure if it is in the next session or two next sessions, but I guess
Yeah.
that it is in the following weeks, definitely.
Yeah, exactly. Like
We will come back to
stochastic.
it too many
Yeah.
times,
Exactly.
for sure.
Yeah.
This is appearing in anywhere, actually, everywhere in the machine learning. One more question. Okay, to me, if we look at the sequence of yns, which is x plus noise, okay? So if you just draw the sequence of those, then it seems that we are having one trajectory, and then start again from the same y0. Let's say that you want just to write down the sequence of the sequence of yn started from y0, okay? Then you have one trajectory, then you can have another trajectory,
For
trajectory.
different realizations of
For different realization of the noise, exactly. And then what this algorithm is doing is just taking just one of those trajectories, trying to optimize over that, something like that. So probably that's the main reason of having poor convergence rate and then having everything very much dependent on the step size. Because it's not that much, well, it is dependent on the step size, but it's a step size per se depends on the underlying variations, which is different realizations here, or let's say different trajectories of this random process. So what would happen if we make it a little bit more smooth? So instead of doing these for every iteration or every realization of the noise, let's say we have 10 realization of the noise and then taking an action.
Actually,
like
there is one result I saw, but I didn't went through. I think it was also mentioned even in the end of this paper that let's say you instead of having just yn here and just decide on the value of yn, let's say you keep track of some values of y, and then you use that to express xn. But I think in this paper he didn't also follow.
No, definitely it's not in this paper. So
No, it's not in this paper. I think I saw it in different literature. So yeah, they were saying that there are approaches that you take instead of only deciding on this, you take record of y and do something like that, taking the average method.
it's very much like batch gradient descent actually. So where
Exactly.
you do have a batch instead of deciding everything based on just one sample.
Then
Yeah.
you still just have a random noise, but it's like a
Absolutely.
noise is
Yeah.
just a little bit, or like the variance is much smaller, I guess.
Yes, exactly.
Yeah, so
it's
exactly.
kind of the
The
same
variance
problem,
will be-
yeah.
Exactly the same problem, but since
But
the
with-
variance
yeah,
is smaller,
with-
probably you will
yeah.
converge a little bit
Yeah.
faster.
Yeah.
Or but with a trade-off, so I don't know. Maybe it could
Yeah,
be
absolutely. You
actually-
should go to infinity. Way to infinity.
So maybe I mean either one extreme is good. Either it's just good to do always just one step, and then or it could be some kind of a one could probably put in the equations. I mean, it shouldn't be that difficult to look at. Okay, what's the convergence if we just do one step always, or if we take like a batch of 2 samples, 3 samples, like average. I think one should.
I
do-
guess that
Yeah.
there should be something in between. So neither
Yeah.
deciding everything based on just one sample or waiting for infinite amount of time to take enough number of samples so as to have absolutely no noise in yn. And then
also
iterate based on
just
that.
one approach. I mean, more dynamic approach could be taking, let's say, one sample and then increase the number of samples as you get closer, so you're not losing your resources for the far values of y. So let's say you take one sample of y
Yeah.
and then you get closer, then you get 2 samples, then if you get closer, this is just something that maybe.
Yeah, absolutely. But then how you can formulate that
Yeah,
problem?
yeah,
No, but I think this
But
has-
this is
this has
this
been
is
done,
something
this
that
has
they
been
do
done.
in
Yeah,
has
absolutely.
been done.
These all have been done.
There was a
for
big
sure.
talk by Elad, I think he was talking about some recent work with his students exactly about that. So trying to pick these samples adaptively. And then as you get close to the
number of
optimal
samples.
solution, you need less samples. Obviously, in the beginning you want to explore, so you take more samples basically. Yeah.
But also, I was wondering, like, for example, if you do let's say you're doing a mean square estimation, or something like that, then when you kind of just, the variance will depend like 1 over n, where n is the number of samples. Like
Yes.
this is the kind of a, if you look at this, will be the bound, kind of the best probable estimation you can get depending on how many samples you have. So I was thinking that, also I was just thinking kind of this kind of intuition, like why you can never, like this kind of upper complexity, this should be a lower bound. Because in the best case, we are not doing any dynamics, we're just doing mean
Yeah.
square estimation.
Or I'm not sure. I think the way they get those bounds, at least in like optimization literature or gradient descent, stochastic gradient descent, usually what they do is like they try to bound the distance between the current iteration xk and then the optimal solution, and usually that will decay like something like 1 over k, and then this is why they say like the decay is proportional to 1 over k, so basically O over k, and this is basically like relating the distance like xk minus x star or something like that. Yeah.
But I think, so my main point was like, I think this kind of
Yeah.
1 over n, that's actually, you should be able to prove it's a lower bound, because even if you're not doing the dynamics, you're just doing the mean square estimation, then this is, you cannot
Right.
achieve better in kind of as a function of samples than this.
Actually, in some
Right,
sense
but
you're
yeah.
right, because
Yeah.
we chose
You have
an
to-
to be one
exactly.
type 1 over n, so it's like an
You're doing an
achievable.
adaptation.
Yeah.
Exactly. You have like some sort of achievable mechanism.
Yeah.
Yeah, exactly. So in that sense, it is something that you can achieve in practice, so it is a lower bound actually.
But it is an
Yeah.
upper bound in the sense of just looking at the an to be of type of something over n. So in this category, this is the best we can achieve.
Or hope to achieve.
Yeah, hope to achieve.
Yeah. Yeah, exactly.
But But one thing for your MSc, now I'm thinking, we don't know what is the final value for theta, right? So it's not like knowing, okay, it's not like sampling so as to estimate just one value. So taking some samples so as to estimate, and then once you have some noise, then the variance would decay as 1 over n. So it's not like that. You don't know the exact value, you don't know the root of that function. So you need to iterate to find the root of that function.
Yeah, but so I would think that that would be a more difficult problem. I think maybe you could construct
Okay.
kind of a you can create this problem to make it be a mean square estimation.
Yes,
And then you will
we
get the
can
lower
do
bound.
that. We can do that as a sequence of mean square
Yeah.
problems.
Yeah.
So then we have at least one problem which you cannot achieve better convergence rate.
That should be
Yeah.
possible. That should be possible.
Actually, I didn't.
Then, yeah.
I didn't went through the proof of here, but the bn is actually that we defined was this square root exactly, and then we take that this is converging to 0. So something like that might be in the heart of the proof for proving this one. That first they characterize the error. Yeah. I don't know. I mean, I didn't went to this literature.
No.
No, that's okay. But usually those proofs are some common techniques for nowadays, not for back in 1960.
Yeah.
Okay, thank you. Any other questions?